Good. Is it working? Yeah? Okay, good.
Okay, our next speaker is Ivan Perez.
Thank you for the introduction, and thank you all for coming. I'm very excited to be here, and we're very excited to show you a new FRP abstraction that we've been working on. So the first question that I want to raise to the audience is, what FRP is? What is FRP? And raise your hand if you really, truly understand what it really is about. And there's a lot of discussion about this. There's a lot of questions. FRP is about meaning. It's about describing what things are over time without regarding to how you sample it, how you gather the data, how you interpolate or calculate. It's just what it means. So here, for instance, we are maybe talking about a value that changes during the execution of a program. And it could be, for instance, the mouse position or the y coordinate of the mouse position. And we can express things in terms of that for all time. And we can say that something that varies over time depends on something else that also varies over time. But the problem with FRP, and one of the reasons why it gives so many people so many headaches, is right on this slide. So if you look at this T over there, you see that we're sampling something that varies over time at arbitrary times. And the problem comes from when we look too far back in the past or we look in the future. If we look too far back in the past, it means we have to remember that past. So this could be, for instance, the signal on the left, the varying value on the left could be the mouse position. And that means we have to keep it in memory. That means if we allow those kinds of expressions in which we sample other things at arbitrary times, we are inherently leaky. Our system is going to leak no matter what. The other problem emerges when we enable access in the future. If instead of saying xt on the right, we say something like xt plus 3 years, that means to understand the value of y now, we need to wait 3 years. And that may not be something that we can realize. If our system is a physics simulation, it may make sense. It's non-causal, it's not realistic, but it may make sense. But if this is user input, we actually have to wait 3 years. So, as I said, this gives many people many headaches. And there's a lot of room for design decisions in FRP. And there's a lot of implementations. And this is just an excerpt of what's available on Hackage. There's a couple of games, but everything else is libraries. And if you're confused at this point, you're not alone. This confuses designers, developers, and researchers alike. And the second most popular FRP Haskell project on GitHub is the FRP Zoo, which only compares FRP implementations so that you can make an informed decision about something you know nothing about. So what we are looking for is not yet another FRP implementation. What we want is a unifying framework, something that can do what other FRP flavors can do and more, and what several of them can do at the same time. And this is what we're going to present. So I'm going to start with one FRP implementation called Yampa, which is very similar to what Paul Liu already explained. It's based on the same ideas. And then we're going to see what the problems are with this and how we're going to find that unifying framework. So this is Yampa. And Yampa addresses the two problems that I mentioned before, which is looking too far back in the past and looking to being able to look in the future by not letting you sample signals at arbitrary times. So you can look at the last sample, you can look at the last known value of a signal, or the present known value of a signal, and that's it. It's causal because you cannot look in the future, and it's efficient and it doesn't leak because you cannot look arbitrarily in the past. You can keep it in memory yourself, but then it's your responsibility to make sure it doesn't leak. So in Yampa, what you do is you define signal functions, which are transformations between a change in input value into another change in output value. And you do that using arrows, which is an abstraction based on monads, a generalization of monads. And you use combinators like these, which essentially allow you, for instance, to lift a pure function or to connect transformations in sequence or to pipe them, put them in parallel and broadcast the same input value to several, etc. So doing Yampa is very similar to circuit design. And see how I'm doing with time. Yeah. So let's try to understand the limitations of a framework like this. So this is a random example of what a Yampa network could look like. We have a bunch of transformations. Here we get an input signal. We pipe it through, transform it, get an output signal. That becomes the input signal of this thing, and that's the output of the network. This is a whole network together. Let's just imagine that, right? And there's one thing that's important to understand about Yampa. It's that all input happens on the left at the same time. Then you pipe it through the network. You pass it through the network, which is pure. It doesn't do any I/O. And then you consume it, render it, show it, whatever. So let's imagine that you need to understand what's going on there. You need to understand that component is somehow misbehaving, but you don't know why, and you need to see what's going on. But you can't do I/O. We said we can't do it. Signal functions in Yampa are pure. So you can't use trace. You can't use print. You can't use any of the normal mechanisms that you would normally use. So your choices are very limited. You can either take a second output from that component and pipe it all the way out, or you can encode the knowledge that you need to debug this in the output signal with maybe exceptions or either or maybe. So you have to change the output type of that component that you have to debug and all the other components that follow all the way to the interface. But this is arrows, and arrows are binary. And that means the arrow combinators are binary or unary. And that means that that's an arrow, and that's an arrow, and that's an arrow, and that's an arrow, and that's an arrow. So when you change the type of these guys, you change the type of that guy, and that guy, and that guy. And this means that you wanted to do something auxiliary and secondary, and that should not impact your API, which is debugging something. Suddenly you have to change the types of your whole program just to debug it. So this is one of the limitations of Yampa. Another limitation is that all of these components tick in synchrony, and you have no control over time. So what we're going to propose is a generalization of Yampa signal functions that deals with these limitations and also allows a bit more control over time and can do things that other reactive frameworks can also do and Yampa cannot do. So if there's only one slide that you will remember, please let it be this. This is our definition, and it's extremely simple. It's very similar to what you saw for signal functions, and it's something that takes an input A and produces an output and a continuation in a monadic context. That's it. That's all. You can go home. So two important things. M is an arrow, and M is a monad, and MSFM is an arrow. And we're going to obtain all the benefits that I mentioned before from this definition. So it's reactive, because we have outputs that depend on inputs, and we use the arrow combinators to express data dependencies. It expresses progress towards the future, because we have continuations and we're going to move forward. And it's versatile. We have added a monad to provide the versatility that Yampa did not have. Notice that there's no time. Time is essentially an FRP, and here there is no time. So this is reactive. It's F, RP. It's functional, it's reactive, but it's not yet FRP. So let's just try to get an intuition of how these guys are executed. It should be very simple. So if you have a bunch of inputs coming from an input stream, what you do is you pass one of them through a monadic stream function, and you get, in a monadic context, an output and a continuation. You take the second one, pass it through, and get, in a monadic context, an output and a continuation. What's important is how these monadic effects are going to be executed. So what you're going to get at the end is the chained effects in that direction from this corner to that corner, and the output list in that order. So let's see, I'm not going to explain all the combinators. There's only 4 slides with 4 combinators that are essential to understand how this works. 2 of them are monadic, deal with monads specifically, 2 of them do not. So one of them is lift S. You saw in previous slides that we had R, which is an arrow combinator that allows us to lift a pure function. into an arrow. Here we provide a slightly more general version, which is lift-s, that allows you to lift a monadic computation into an MSF. Essentially, you take the input here, the x, and you can do whatever with it. This is a monadic in the IO monad, and then you have to return an output. So this is pointwise application, meaning that the continuation of this MSF is the same function. So what it does is it applies this function in the argument to every input that comes in. So if you look at this diagram, it applies that function here and here and here, always the same one. You can connect things using the arrow. This is similar to function composition, but it's a generalization for arrows. So you can pipe things, you can connect them in sequence. And what's important is that we just added monads. And monads may not be commutative. So effects can matter. And if they do, the order of those effects must be conserved by this combinator. So if we have an MSF that, for instance, has only this side effect of reading input text, and it doesn't really consume any meaningful data, but it does produce numbers. And then we have this function that we had before that consumes integers and produces bools and has side effects. We can connect them like this. And this effect is always going to happen before this one. And this is going to be one MSF, and what will happen is we'll get this effect, and then this one, and that one, and this one, and that one, and so on. So as many input samples as we have will repeat this sequence. To understand this input, the red means that the user is typing this text. So if the user types the text 7, that's not an even number, so nothing is printed. And this is a negative, that's not a negative number, so this MSF doesn't print anything. And this is a negative number, and this MSF, which try to detect when the input is negative and give us some kind of message so that we can debug things, will print a message. So we just show that this framework is enough to address the problem of debugging reactive networks that we had before. So there's only two more combinators that I'm going to explain. One of them is what happens when we add monads, when we start adding monads. The IO monad is a bit dangerous to add, so I prefer to stay away from it as much as possible, but you can add something like writer to achieve the same effect that we wanted to do, which is to debug what's going on. And what you can do is implement debug even here, but instead of using print, you use tell, and you store this string in the writer log. So at the end of each run, you will have one or more strings that tell you what happened inside. The problem with this is how you run it, right? Because if you run several steps of the same MSF in this monad, what you get at the end is the log for all the steps in sequence. But you may want to consume it at the end of every step. So what we provide is a combinator that allows you to get out of this monad for MSFs. This is very similar to run writer T of this transformer, or run writer of the writer monad. But what it does is it applies it at every step. And it gets the thing inside and it gives it to you on the outside. So we're essentially removing one layer of the transformer stack. So this is about nesting effects and then removing them. And finally, and this is the very last one, I promise, this is where things get more interesting, which is what happens if you plug other monads. The writer monad is very trivial, but what happens if you plug maybe? Maybe can give you something or nothing. So if you plug it in the signature of in the type, you see that you may have a continuation or nothing at all. You may have no output and no continuation, which means that's an MSF that terminates. This is similar to tasks in Yampa. It's similar to monadic FRP by van der Ploeg. And all we had to do is plug a different monad. If you use the standard from maybe or run maybe T, you'll get this behavior. And this is one example of implementing a similar thing that we had before, but using maybe T to terminate. And what we do is we have a guard, and this is a monadic action in the maybe T monad. And this becomes nothing when the guard is not fulfilled. So when we recover from this, when we get out of this maybe t transformer, and we get out a maybe value, it will be nothing if this guard was not met at some point. So this will be an MSF that terminates. But what we want is to recover from that. Not only to terminate, because then you run your program once. Once it fails, it stops. But you want it to recover. And we provide a different combinator, which is catch, that allows you to determine what will happen once this becomes nothing. So it eliminates one transformer from the stack once again, but it allows you to state what will happen then. Now, this may seem like a lot of combinators, but they all have are instances of one similar interface. And it uses only 2 type classes to implement this. What happens if you plug other monads? With either T, you get switching like in Yampa. With list T, you get parallel tasks, parallel MSFs with broadcasting. So what you get is an MSF that can branch into several MSFs and can branch and then it can die. So if you have in a game, for instance, a ball that's falling and you shoot it and it splits in 2, that's an MSF that just became 2. And you get that for free by just defining a couple of instances for list T of 2 classes in our library. With state T, you get global state, obviously. With reader T, you get a global environment. And this is where things get interesting. Because we promised something like Yampa. Well, Yampa has, signal functions in Yampa have this signature, in which this represents the time that passed since the last time you look at the system, the last sample. And we can do that if we put it here. That's all. If you expand this, it becomes exactly that. So all we need to implement Yampa is this definition. All the core definitions, all the primitive definitions in Yampa are things that we provide also for our framework. And we just need to add integral, which is one signal function that integrates the input and provides the integral in the output. That's the only primitive combinator or signal function in Yampa that depends on time. Everything else is reactive, but not FRP, not time dependent, which is telling us something about Yampa as well. And now this seems very simplistic, but we actually tried it. There's one example in the paper, which is Pong, unidimensional Pong, which is very simple, it's just to illustrate things. But we tried it with a real game. And this is a game that is online, and you can try it. And it's Breakout. It's, well, real game, sort of. But it uses Wiimote, which is the Wii console input device for interaction. You can also use Kinect, and it detects you, and you have to dance around and move around so that it follows you, and you are the paddle down there that moves. And it works on Android, it works on Linux, it works on Windows, it works on Mac. And the performance that we get is very similar to Yampa's. So the performance that we get with this is about 10% slower than Yampa, but Yampa is optimized using GATTs, and our library is not optimized at all. So we hope that things will get better with time. And if you look at the memory profile, it actually goes down. It's not even flat. It goes down. As you remove blocks, you remove elements from a list, and it starts going down. And then it spikes up again when you move to the next level. And we tried it with a slightly, maybe simpler, but in some way also more complicated game. This is a commercial game. And you can buy it on Google Play. And it's implemented in Yampa. And it's a board game, so it makes it, the gameplay is simpler. But it has to deal with all the nuances that you have to deal with when you provide a professional application, which is saving preferences, dealing with records, with the fact that you can get a phone call where you're playing and the application has to stop temporarily, but then recover, and all of these things. And this, again, works with our framework. So what we have in both of these programs is a flag in the Cabal file. And all you have to do is compile linking against Yampa or linking against our library. It's a full replacement of the primitive Yampa, of the primitive combinators in Yampa. And finally, this is only what we do about Yampa, or how we supersede, at least in some respects, Yampa. But we can do a lot more. Yampa's signal function is very strict. It doesn't allow us to do anymore. But we can define Yampa signal function with an extra M and put it here. If you put identity, you get Yampa. If you put something else, you get something better than Yampa. We can do things that Yampa cannot do. For instance, we can do continuous collision detection with a special monad. So if you use the writer monad, and what you do is in the log, you put a time. And that's the next time that is going to be important in your system. If a ball is going towards a wall and is going to impact, it can signal that in 3 seconds it's going to hit the wall. And if you don't look in 3 seconds, when you look, it's going to be deep inside the wall or maybe already on the other side. And that creates tunneling effects or bullet-free paper effects, in which the ball just continues on and on. And you can let the implementation of the ball say, no, 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 I want to store 3 seconds in the log, and the output, when you run the whole network, you know that in 3 seconds you need to look at it. And if you use minimum as the append operation of the monoid for the writer monad, what you get is the closest time that any signal function needs to look at. And then you reevaluate the whole system at that time and give every signal function a chance to state again what's the next most important time. We can do reactive programming. And when I talk about reactive programming, I mean the traditional imperative kind of reactive programming, because we have the monad. We don't actually need to gather inputs from the input of the signal function. We can take them from the monad. So we can define streams and sinks and connect them, and we have an implementation of reactive programming that is also push-based by using a different evaluation function that knows a little bit about how push works instead of pulling. If you know a little bit about FRP, there's push and pull, and you will understand what this is. There's also classic FRP in which you talk about signals, not signal functions. And we can also do that by combining this with this. What we get is streams that vary over continuous time. That's more or less what classic FRP is. But what you get is that it's very similar to what Yampa already does. You can use all the operators that you can use, all the combinators in Yampa, and you can use the similar style. But you can also use applicative style and have something that looks a bit more like what you will intuitively think about. And I promised that we wouldn't sacrifice anything in Yampa. Yampa is pure. These things are arrows. You can use the arrow laws and transform things and reason about how they work. And here, we're keeping the type. The M is explicit in the type. We're not hiding it. And that's crucially important, because that means if you have an MSF in your program and it doesn't have I/O here or anything that hides I/O, then it doesn't do I/O. You never lose those static guarantees. So you can reason about what happens. We have proofs that these guys are arrows. And if you can constrain the monad to get additional properties, for instance, if the monad is commutative, the arrow is commutative. And we have a proof of that. And that means we may be able in the future to apply the optimizations of commutative arrows to our framework. If the monad is an instance of monad fix, then this is an instance of arrow loop. Everything's in the report, in the paper, so please go ahead and read it. And if you want to play around with this, if you can think of different monads that you may obtain funny behaviors with or unexpected behaviors with, then please go ahead and tell us. We'll be around. Manuel, one of the co-authors of the paper, is also right here. So we'll be very happy to discuss these things with you. And that's pretty much it. It's all online. You can download it. I'll be happy to take any questions that you have now. Thank you. Yes.
Hi, quick question. The type you end up with looks pretty similar, I'm not sure, with the kind of types you have in library like pipes.
Yes.
So does that mean that you could build Yampa on top of pipes directly?
Yes. Yes, we think that's the point. But pipe signature, well, he has been reading about this all night so that he could answer your question. But as far as I understand, pipe signature is a lot more complicated. And that means for the new user who is trying to do FRP, using pipes is not going to feel so intuitive. So I think you can definitely do this in pipes, and we may be able to do pipes in this. We don't know about that. We still have to check, but we may be able to get a lot of the things that pipes has in this. It also means that this is, if you can implement this in pipes, then this is the missing link. And all of those things that you get with this simple abstraction, you can also do in pipes very easily. So, yeah.
Thanks.
Thank you.
Andrew Cowie, Commonwealth Bank. One of the things I'm battling my head against right now is in time-varying situations is uncertainty in time. So most of the things we do in computing have this sort of assumption that at time with infinite precision, something happened and then we all react to it. I mean, the example you gave was bump into the wall in 3 seconds. But
yeah.
for signals coming out of the environment,
yeah.
There's noise there. And maybe this is more a general FRP question, but how do you deal with noisy variation on things like time or other inputs?
So I'm guessing this question has a bit more to do with events and behaviors in FRP.
Quite possibly.
So the idea is that sometimes you have something that happens at a time and only maybe lasts for a fraction of a second, and you don't know when that's going to happen. So either you sample regularly or you have some other mechanism that will wake you up when that happens. That derived into 2 FRP flavors and a lot of intermediate implementations, push-based FRP, in which when something happens, you'll be executed and updated, and pull-based FRP, which is what Yampa does and what we do in principle, even though we do some push-based. But in principle, what you do is you sample regularly. So what we do to deal with those is just sample fast enough.
Thank you.
Thank you for the question. Any other questions?
All right, let's thank the speaker again, and then we have a break.